good morning or good afternoon, depending on where you're calling from. My name is Charlotte, and I want to welcome you to today's webinar, Architectural Patterns for High-Performance Microservices in Kubernetes. Before we begin, we do have a couple of housekeeping items to go over. Everyone will be muted for the webinar, so please type any questions you may have as we go along into the Q&A panel, and we'll answer as many as we can at the end of the presentation. Also, this webinar session is being recorded, and it will be sent to everyone via email following the webinar. Now that we've taken care of that, I want to thank you all again for joining us. Today's webinar will be presented by Rafael Lesko. Rafael is a cloud-native team lead at Hazelcast, author of the book Continuous Delivery with Docker and Jenkins, trainer, conference speaker. He specializes in Java development, cloud environments, and continuous delivery. And with that, I'm going to pass it off to you, Rafael, to get us started.
Thank you, Charlotte, for the introduction, and hello, everyone. Thank you for joining. I'm really happy that I can speak to you right now. So the talk is titled Architectural Patterns for High-Performance Microservices in Kubernetes. And in this talk, I will show you how you can improve the performance of your microservices, basically using different topologies of in-memory store and in-memory computing. I will show the first slide with a lot of things about myself, but Charlotte already introduced me, so you already know everything about me. I'm speaking to you now from Krakow, from Poland, from my apartment. Few words about Hazelcast. So Hazelcast is a distributed company, and we are distributed in two meanings, actually. First, we produce distributed software. You may know us from Hazelcast IMDG, which is what we call like a Swiss knife for distributed processing, distributed computing, for caching. Another product is Hazelcast Jet, which is a library for stream processing. And our third product is Hazelcast Cloud, which is Hazelcast as a service. But we are also distributed with it has a second meaning. We are distributed because we always all worked remotely. So I'm from Krakow, but I'm the only employee from Krakow. We have people all over the world. Our agenda for this talk is pretty straightforward. So there will be a short introduction, what I mean by high performance and why the performance is so important in Kubernetes and microservices. And then we'll walk through the patterns, the topologies that you can use to speed up your microservices. So we'll cover them all. You can think, some of them you may already use in the caching solution. So you may already find your system in some of them. And that would be good, actually good if you find yourself somewhere there. And at the end, there will be a short summary to sum it up. So let's start with the introduction. So the performance in microservices. So why is it important? It's not even important, it's like critical nowadays because we build microservices systems and we have a lot of microservices. So systems have like Netflix has over 1,000 microservices. So if all of them are not performing so well, in result, the whole system is super slow. So that is why it's super important to keep every microservice with a good latency, with a good performance. But also the second thing is that if we speed up our services, it means that it allows us for more complex use cases. So we now can apply use cases that were before not visible in microservice architecture, like AI processing, mind framework optimization. There are a lot of other use cases you will find it on your own as well, that, you know, if our system was faster, you could do it, you know, we could implement it using microservice architecture and deploy on Kubernetes. And the last point I mentioned here is cloud cost optimization, because even if your performance of services is good enough for your end user, speeding up your system means you will pay less for the cloud. Like if you use less CPU, if you use less memory, it just cuts off the cost of your system. That is why it is so important. So high performance is no longer like a nice to have feature. It becomes nowadays like a must. So we cannot compromise on it. So that is the message actually of this talk. Now, how it looks like in the microservice world. So how can we achieve the performance? So let's see the first diagram. So that is a classic microservice-based system deployed in Kubernetes. So we have a lot of services. They are written in different programming languages. They have versions. They use each other. And there are a lot of them. So now the question is, how can we improve their performance? So we normally can, do a lot of things like we can do like some in-memory databases, some caching, some streaming platform, distributed computing. And if we combine it with Kubernetes, actually we can see that there are really a lot of options. That is why I would like to structure this somehow. So firstly, what we can do, we can embed like a library into each of the service, like a caching library. So you can embed caching to each of the service. Perfect. You then use caching or any in-memory store to speed up your computing. What else can you do? Second thing, you can deploy an in-memory data store or in-memory computing platform as a server, and then use client-server architecture to use this computing power or in-memory data store from your services. And finally, you can use something, you can use like a reverse proxy, that anything like reverse proxy caching, that the request before it goes to the service, it will be cached, or you can do something else as well. But you do something with the request, so the service is not even aware that speed up was done to it. And that is what I basically will talk about, these patterns, but in more details. So the first thing, you can use something embedded. So we can embed a library to our service to make it faster. How it looks like. So imagine we have a system like that. A request goes to our system, it goes to the Kubernetes service, it's load balanced to one of the Kubernetes pod, and inside this Kubernetes pod, it's an application that receives the request. Now an application uses some library. Classic example, it would use a caching library to use to check, okay, have I already executed such a request? If yes, use the cache value. If no, do some processing, put it into the cache, return the response. So if we think about this example of caching, this is very simple. I mean, caching is simple, so we could even, if we want, we can even implement it on our own. If you like Java, that is how we could implement it. So we could have a concurrent hash map as a cache, and then every request goes to the process request method, and then we first check if such a value is already in the cache. If yes, return the cached value. If no, do some processing, do some business logic, then put the value into the cache and return the response. So you could implement a simple caching on your own using a standard collections, but you better not do it. So implementing any optimization like this is actually not a good idea, because like Java collection or any collection in any language is not good as a cache, because it has no eviction policy, no max size limit, no statistic, no built-in cache loaders, no expiration time, no notification mechanism. So basically it misses a lot of features that we would expect from a good cache. So what would be a good cache library? For any programming language, you will find one. For Java, for example, Guava is a very good caching library where you can define all these features that are lacking of the Java collections. You can define them upfront. Another good example is EHCache. Now we can move this caching idea one level higher, like one level of abstraction higher, and put the caching into our application framework. So in case of Java, most people use Spring. So that is how we could cache a response and speed up our service. So with one keyword cacheable, we could say that now every call to the method getBookName by ISBN first check if the given ISBN is found in the cache called books. If yes, return the cached value. Only if it's not found, execute a method find book in slow source. But be careful because Spring, for some reason, it uses concurrent hash map by default. So you're better off changing this cache manager to something like Guava or some other proper caching solution. So we ended up like with this diagram. So we have embedded, usually it would be embedded caching, but you can think about some embedding some in-memory store or something else to speed up your service. Now, what is the problem with that? Like, what is the problem with this diagram? So the problem is that imagine that a request goes to our system, it goes to the Kubernetes service, it's forwarded to one of the applications. Let's say the first time someone calls our system, it's load balanced to the application on the top. So, okay, we do some business logic, we put value into the cache and return the response. So far, so good. But now, let's say that the same request goes to our system, and now it's load balanced to the application at the bottom. It may happen because like Kubernetes service, it uses just round robin load balancing, so it can forward your request to basically to the random pod. So what happens now? This application at the bottom needs to do this long-lasting business logic once again, because these caches, these libraries, they don't know about each other. That is why one of the improvement of this pattern of embedding something that can speed up our service would be to use embedded distributed library. And here is where Hazelcast comes in. So Hazelcast is a library for distributed computing. You can use it for distributed caching. So now what happens here? The flow is exactly the same. However, each cache in each application, now they all form one consistent caching cluster. So no matter which library you use in which Hazelcast pod, you will store the data in the same database, actually. How to use it? How can you change your embedded library to embedded distributed library? So if we stick to this example with Spring, all we have to do is change the cache manager and define, okay, from now on, I would like to use Hazelcast cache manager to cache my entries, and that's it. All the rest of the code is exactly the same because Hazelcast is compatible with Spring. Now, let me show you a quick demo on this, how it looks like in practice. So I have here my application. By the way, all these demos, I will share with you a link to all this demo. So if you look at this, there's nothing so interesting here. What I would like to see, so we have our book service. We have our, actually I wanted to show you, this example. So in our service is, in our service, there is nothing interesting. We simulate like a long processing with a sleep, and we have this cacheable. So any call to this method will first check if the value is found in the cache. Now I have my cache configuration, which, as I told you, it's just a configuration of your cache. So in case of Hazelcast, you just specify, I would like to use Hazelcast cache manager. That's it. Now, let me run this application on my laptop. I will run it with 2 instances to show you something. First thing you will see, it's like slow because Java Spring, if you are used to Java, it takes some time for the startup. But that's not what I wanted to show you. I wanted to show you something else. So let's wait for the first application started. We already see this log means that embedded Hazelcast started. So we have an embedded Hazelcast inside our Spring application. Now the second application is starting. And what we will see in a second, that it will try automatically. Yeah, it joined this log means that the embedded Hazelcast from one instance and embedded Hazelcast from another instance, they formed one consistent in-memory data store cluster. So they are acting like one database or one cache in this example. Now, what is interesting? So the interesting thing is that I didn't specify any configuration, but they found themselves. So now you can think how it is possible that I didn't specify any configuration, but they found themselves. So in my case, I've just run it on my laptop. So they used multicast to discover themselves. So laptop is a very, very easy environment. But what about production? You will not run production on the laptop. So how it looks like. So we thought how to make the discovery easy for the users so that you don't need to really configure much. And as a spoiler, I will tell you that the same configuration would work on the production Kubernetes cluster. Because what we did, we created a bunch of plugins for each environment. So if you run in the cloud, on AWS, we have an AWS plugin. If you run on Kubernetes, it uses Kubernetes plugin. And this plugin uses Kubernetes API to discover other Hazelcast members. Now, Hazelcast itself also checks, come on, maybe I'm running in Kubernetes, so I should use Kubernetes plugin. So if you just start Hazelcast with the same configuration, it will say, okay, am I running Kubernetes? Yes. So let's use Kubernetes plugin to discover other members and form one cluster. And that's it. So the same configuration will work on Kubernetes. Obviously, you can configure a little more if you would like to. You may have one Kubernetes cluster, but you would like to set up multiple Hazelcast clusters. Then you can tweak this configuration. If you're interested in more details how to set it up, we publish a lot of blog posts. Also, we have a site called Hazelcast Guides, which actually shows step-by-step how to use different scenarios with Hazelcast on different environments. Okay, so we ended up with a diagram like this. So let's now think about pros and cons of using embedded and embedded distributed solutions. So what was good about it? So configuration was very simple. So because the way embedded in application, you don't really need to define any configuration for it to work. We have very low latency data access because in case of embedded, it's like the same process. So it's super low latency. In case of the distributed, obviously we have some network communication, but this network communication is usually local. So the latency is still good. And we don't need any ops team needed because it goes together with application. You pack your application as a Docker image, and then that's it. You don't need to set up some servers or anything. Now, from the downsides, the management is not flexible. Imagine that you would like to scale up your Hazelcast, but not scale up your service. You cannot do it. It's limited to JVM-based solution. So Hazelcast, you can embed it into your JVM applications, but not really into your Ruby application, for example, or Python or C#. And from the downside, I also mentioned that data is collocated with the application, which may not be a problem, may be a problem, depending on your security policies in your organization. Okay, we covered embedded patterns. So let's move on. The next thing I would like to show to you is client server. So client server is like a good old database style. So we set up server separately and then use clients to connect to the server. That is how it looks like. So flow is now as follows. Request goes to our Kubernetes service. It's load balanced to one of the Kubernetes pod and to the application container inside. And now application uses a client to connect to, in this case, to Hazelcast, to like in-memory platform, to cache, whatever you use it for. You can use it as, because as I told you, Hazelcast is kind of a Swiss knife for distributed computing. So you may use it for a lot of scenarios. You may use it for computing, you may use it for in-memory storage, you may use it for caching, and so on. But the point here is that you set up Hazelcast server, Hazelcast cluster separately, and you use Hazelcast client to connect to this server. Now, how this diagram is different to the comparing to the embedded mode. So there are two main differences. First thing, we have something new in our diagram. And this something new, this server requires some maintenance management, and it's good and bad. I mean, from the good sides, you can scale it up as you want, not touching your application. But it also requires, setting up some security, doing some maintenance. I can already tell you that in big enterprises, what we see is that this is managed by a separate ops team. But there is also a second difference when you compare this client server to this embedded diagram. And the second difference is this part. So we use now a client to connect to the server. We use a client, which means that we are no longer limited to this using the same programming language. So in case of Hazelcast, you're not limited to JVM. You can use whatever programming language you want, because there is a well-defined protocol between client and server. And that is a very common pattern that you set up your database, and you use a lot of applications, a lot of services written in different programming languages, and they connect to this in-memory computing platform. So that is like a very good. I mean, that is what we see. It's like very, very widely used. Now we are in this Kubernetes world. So how to set it up? So how to set up Hazelcast and your application connecting to this. So setting up Hazelcast server is actually very simple, because in Kubernetes, you can use one Helm install command and that's it. If you don't like Helm, you also provide an operator, so you can use operator. If you don't like operator, you can write a few Kubernetes configuration and set it up on your own. So that is the server part. Now how to connect with the client? So that is how the client configurations looks like. So it looks, you don't need to configure anything, because Hazelcast will find its way to discover this Hazelcast server. But if you have multiple Hazelcast servers, then you may explicitly say, hey, Hazelcast configuration, use Kubernetes plugins with this and that parameters. But it's also very straightforward. And that's it. Your Hazelcast will connect to your client, will connect to the cluster. Now, this is an example for Spring and for caching, but obviously you will not only use Hazelcast for caching. If you just ignore the Spring and everything, if you would like to set up a client, that is how it looks like. So we specify, okay, you create a client, get me a map, and then you can, for example, put some value into this in-memory storage, or you can execute some computing. or you can use some stream processing, etc. So you may do a lot of different things with this setup. Now, we already moved the, as I told you, like what we see in big enterprises, this server part is usually maintained by a separate team, by a separate even department, but by something else in your organization. So if we already moved this server part outside our application to somewhere else, we can even make one step further and put this server part into the cloud. So cloud is kind of a client server, but it's very specific because the server part is maintained outside your organization. So the diagram is very similar. We just don't need to think about so much about internals of the server part. We also don't need, we don't need anyone to maintain this part. We don't need separate ops team, but we pay for the cloud provider. So the same idea like the cloud-oriented programming idea. So how it looks like in Hazelcast, I will show you in a second. So we will create a cluster, Hazelcast Cloud, and then we will connect with the client. So this is how your client configuration, our client configuration will look like. So we specify, okay, use cloud config and use the discovery token. The discovery token, you take it from web console or from Hazelcast Cloud CLI. Set up cluster name, that's it. Hazelcast client will find its way to the server part. So let me show you how it looks like in practice. So let me stop this application. And so this is a Hazelcast Cloud console. You can create an account for free, and there are some free clusters, so no problem with that. So we can create like a Rafa cluster. You can set the underlying cloud provider, you select the regions you would like to use, you specify, okay, how big should my cluster be? You can enable persistence. There are a lot of options here. Finally, when you click create cluster, it will start to create the cluster. And in the meantime, while the cluster is being created, let me show you how the code will look like. So our code will be this one this time. So this is exactly, it should be exactly the same what you've seen on the slide. So I call the Rafa cluster, and this is exactly the config. I will use the same Spring application, but you get the idea. It doesn't need to be Spring. It will not change anything. But in this case, we'll use cache configuration with the Spring using Hazelcast Cloud. Now I need this discovery token, and I will take it. Okay, my cluster is already created, so I can click configure clients. And from here, I can take my discovery token and copy this into my Spring configuration. And if everything is fine, then we can start the application. So it's the same application, no really much logic here. We just changed the underlying cache provider to use Hazelcast with client server, and the server is located in the cloud. So it's starting, and we already see, okay, it discovered the members in the cloud. So everything is good. Now, there is it works quite smoothly. You can try it on your own. As I told you, you don't even need to create an account on Hazelcast Cloud, because if you I can show you, it's like it's pretty straightforward. If I go from here, so you can go to cloudhazelcast.com and sign in with your GitHub or Google account. That's it. You will be able to create free clusters. Now, I want to show you one thing. So everything is fine. It will work. Our application is good. Now, there's one problem here. So I created this in my cluster is created in London. And as I told you, I'm speaking to you from Krakow. So, there's some distance between London and Krakow. So this is not a good actually scenario for caching, because like, what is the point of caching if I cache something from Krakow and use the store which is located in London? So it doesn't make so much sense. That is why, actually, no matter if you use cloud solution or client server, you need to think about where your server part is located. And first thing, you need to think about, okay, if I use Hazelcast Cloud, I should select the same region where my client will be located. This is the first thing. Second thing, when I was creating a cluster, I was selecting the underlying cloud provider, because we, as a Hazelcast, we don't provide like machines. We use AWS, GCP, or Azure. So now you should use the same cloud provider that where your applications are running. So if you run on EKS on AWS, then you should select here, okay, I would like to my Hazelcast Cloud cluster to be deployed on AWS, because you don't want to go in between cloud providers, use some public network, because it is just slow. But that is still not enough, okay? Because remember, in this in-memory computing is a very low latency domain. The requirements for latency are even more strict than the database. That is why we need even something more than the same underlying cloud provider and the same region. And this something more is we have an option for doing the VPC peering. So you can do a peering between VPC where your application is running and the VPC where we provided the cluster for you. And this way, they are in the one logical local network, like virtual network. So there's not even one router hop in between. So that is the scenario we need to set up. Now, coming back to our slides. So a short summary about client server and cloud solution. So what is good? So data is separated from the application. That is good. You have separate management. So if all of a sudden you would like to scale up your cluster, your database, then you don't need to touch your application. And it is programming language agnostic, because we use well-defined protocol between client and server. From the downsides, we need some ops effort or pay for the cloud solution. Latency is higher. It's not necessarily actually higher, but you need to think about latency. So this is exactly what I explained to you. If you use cloud solution, do these three things. So the same underlying cloud provider, the same region, and the same and the VPC peering. If you set up on-premises server, make sure that it's in the same local network. You don't want to jump your network calls, to have a lot of network calls between your application and your server. So you need to basically configure this right. Okay, we covered client server and cloud solution. So now, next thing I would like to show you is Sidecar. So, client server is like a very old idea. Embedded is an old idea, but Sidecar is something new. Sidecar came with the containers. It's not only in Kubernetes, but nowadays people talk about sidecars mainly in Kubernetes, but it's not limited to Kubernetes. It's limited to the container-based environments. How it looks like. So this is our diagram. Request goes to our system. It's load balanced to one of the Kubernetes pod. And this time in the Kubernetes pod is not only the application container, but we have an additional container, a so-called sidecar container, where is our in-memory database container. So in case of Hazelcast, you will have Hazelcast server. Hazelcast server running as a container. And now the application, the thing about Sidecar is Kubernetes guarantees that the Sidecar container and the application container, basically all containers running in one Kubernetes pod, they are deployed on the same physical machine. So you know that your in-memory database container is close to your application. That is very good, because remember, we need to think about latency. Now, the other thing is that Kubernetes guarantees that your Sidecar container is available in the localhost. They basically share the networking. So that is another good thing, because we don't need to think about any discovery. We just say, okay, connect to the localhost, and we know that this server is there. So this solution is kind of somehow similar to the embedded mode, but it's somehow similar to the client-server mode. It's similar to the embedded mode because we know that we use the same physical machine, and we can scale up. They scale up down together, and there is no discovery needed. But it is also similar to client-server because we can use now different programming languages. Because after all, we use cache client to connect to cache server. It is just that the cache server is located at the localhost. That's it. So it is kind of in between embedded and client server. How we would configure this? So this is your client configuration for Hazelcast. So you set up a static address, which is localhost and a default port. But after all, your whole system is not static, it's dynamic. You just know that your server will be deployed together with your application. How the Kubernetes configuration looks like. So this is our Kubernetes configuration. So we basically have two containers in our pod, and one is our application container, and the second one is Hazelcast server. Short summary of the Sidecar. So what is good is configuration is again simple because we just deliver application together with the storage, with the database. It's programming language agnostic. We have low latency, and there is some isolation of data and applications. Isolation is at the container level. From the downsides, we again do not have flexible management, and the data is collocated in one application pod, which may not be a problem, may be a problem depending on your security requirements. Now, the last thing I would like to show to you is on this presentation is reverse proxy. So it's mainly used for caching. So you use like reverse proxy caching, and how it looks like. This is something completely different because so far we've seen no better like embedded mode, client server, or Sidecar. So far, the application was always aware of this caching part, the database part. It was just aware what is going on. Now we will make the application not aware of this caching, basically. It will be reverse proxy we'll use mainly for caching. How we'll do it? So this is our diagram. So request goes to our system. It goes to the load balancer, and now just before load balancer, after load balancer, or actually in Kubernetes, you can even implement it together in ingress, because ingress is implemented as nginx in Kubernetes. We have a caching part. And now if we already have such a request executed by our system in total, then it's found in the cache, and the cached value is returned, and the request does not even reaches the application. a very good solution for this is Nginx, because Nginx is a very mature thing, and it's very well integrated in Kubernetes. It's even used internally in Kubernetes, so you can easily use it. That is the configuration, the minimal configuration you need to add to your Nginx server to provide the caching functionality. So Nginx is very good at mature, but it has some drawbacks. So it is only for HTTP, which is probably not such a big deal because microservices are usually in HTTP based, but it's not distributed. It is not highly available. That is and these points are a bigger problem. And the data is stored on a disk. Actually, in Nginx, the data is not stored on the disk, but it can be offloaded to the disk, which may give you some higher latency, which is, for example, in Hazelcast, we don't store data on the disk at all. So you are guaranteed that your data is in memory and therefore accessed with very low latency. Now, the last variant of this pattern would be to use reverse proxy sidecar. So how it will look like. So the last pattern I would like to show you is like reverse proxy sidecar caching and how it looks like. So request goes to our system, it's load balanced to one of the Kubernetes pod, but now inside the Kubernetes pod, it is not the application that receives the request, but we have something like an interceptor of the request, which contains the caching server, and it first checks, okay, do I have such a request cached? If yes, return the response and do not even touch the application. Only if the value is not found, it's forwarded to the application. And obviously all this reverse proxy containers, the servers, they form one consistent cluster. Now, this whole idea, no matter if it's reverse proxy caching or reverse proxy sidecar caching, this whole idea that application is not aware of the server part, it is somehow good, somehow bad. I mean, it has some benefits and it has some drawbacks. So let me first speak about like good things. What is good about it? So you remember this diagram from the beginning of the presentation. So we have like a lot of microservices, they use each other, they're in different versions, that they are written in different programming languages. There's a lot of things happening here. And that is obviously a small microservice system. You remember Netflix, they have more than 1,000 services, and each service has a lot of versions. So now, with this reverse proxy approach, we can look at the diagram like this, do some measurements, see to decide which service is slow, which one is slowing us down. And we can say, I would like to speed up these two services. And you can introduce this reverse proxy layer without touching your services. So that is the whole thing. You, in a declarative manner, on the configuration level, you specify, I would like to speed up these two services. And that's it. You don't touch the code. You don't touch anything else. So it's very safe, very elegant way. And that is actually the reason why you will use reverse proxy sidecar caching. It's like you don't want to mess up with like the services themselves. How the configuration of this would look like? So usually what we will see in this, like if you need to add, in general, if you need to add as a sidecar, as an interceptor, you will need to also have one init container. So how it looks like. So first, like maybe starting from the bottom this time, we have our application container with our business logic. Then we have our interceptor, our cache server. And then we also need some init networking. It will be a script which will change the IP tables so that the request is not received by the application, but by caching proxy container. That is the purpose of init networking. And if you, so that is how it will look like. And if that is like the whole idea of this reverse proxy sidecar, it's like the whole idea of service meshes also, Istio, that is how it acts. I mean, Istio also adds an envoy proxy sidecar to modify your system in a declarative manner without changing your services. That is the point of service meshes. But I also told you like this whole idea, reverse proxy application being unaware of the caching. It has also some drawbacks. So if you think like the caching example, and you think like, what is the biggest problem with the caching in general? What is the people having problems with caching? What is their problem? And if you look anywhere on the internet, what is the issue? Everyone will tell you the same. So the hardest part of caching is cache invalidation, meaning when to decide that the value stored in the cache is already stale. I should not use it. It's outdated. I need to go to the source. And if you use, like, if your application is aware of this caching part, you can use some business logic to say, okay, if this happens, then evict this value, or you can trigger this somehow. But if your application is not aware of the server part, then all you can do is basically to use some HTTP caching mechanism like timeouts, e-tags, basically timeouts. So that is the biggest problem of the reverse proxy approach. Short summary. So what is good about reverse proxy? So it's configuration based. That is the reason why you will use it. So that is the whole beauty of reverse proxy approach. So there is no need to change your application. It's obviously programming language agnostic. It's everything agnostic. Application is not even aware of the reverse proxy. And it's very consistent with the containers, microservices, service meshes. That's I believe that will be the future. From the downsides, we already mentioned, like there is the cache invalidation becomes difficult. There is no mature solution yet for this. And I mean, for the sidecar, for the just reverse proxy, Nginx is a very good mature solution. And it is implemented at the protocol level. So we covered all the patterns, all you can do for your system. So as a short summary, if you happen to think where to put your cache in your system, which topology, or how to speed up where to put your in-memory store, how to do it, embed it, or should I have like in-memory computing server separately? I thought that a useful thing to do would be to draw a very simplified decision tree that you can use to help you decide. So a first thing I would ask is, does my application need to be aware of the server part of what is happening? If no, am I an early adopter? If no, use reverse proxy caching. If yes, use reverse proxy sidecar caching. Now, if your application is aware, it needs to be aware, or you just need something more than caching, like you need some storage, you need some computing. So our application basically needs to know what is going on. Then the next question is, do I have a lot of data on security restrictions? Or if no, do I need to be language agnostic? If no, use embedded distributed. If yes, you use sidecar. Now, if you use a lot of data, you need some complex computation, some security restrictions, then the last question you need to ask is my deployment cloud? If no, use client server. If yes, use cloud solution. So this is like a maybe oversimplified decision tree, but it at least can give you the direction where to look, where to look on. And as the last slide, I would like to share you some resources. So you can find the code samples for this talk. So the demo I presented is in this repo. The second link is a blog post from Hazelcast or on how to set up Hazelcast as a sidecar container. Third one is our prototype for reverse proxy sidecar caching. And the last one is a very good video talk by Nginx which discusses using Nginx as a reverse proxy caching. And with this last slide, I would like to thank you for listening. It was really a pleasure to speak here. And now, if there are any questions, I'm happy to answer them.
I'm glad that you are happy to answer them because we have quite a few that have come in. So let's go ahead and get started. So the first one is, will Hazelcast distributed database cluster maintain separate DB schema for each microservice, which is recommended principle for microservice?
Yeah, I mean, you can, if you think, short answer is we don't have schemas, but we have like map names, so it's more or less the same. So you can use different. Basically, you can. I had somewhere the slide like get map and you gave here a name, and now you can use different names for different microservices. So this is one approach, that you deploy one Hazelcast clusters, a lot of microservices, and obviously they should not share the same using the same map or the same data objects, because then what's the point of microservice architecture? But another deployment model is that you set up a Hazelcast cluster per microservice. So it's the same idea as databases. So you can set up a separate database for each microservice, or you can use separate schema of the same database for each microservice.
Perfect. Thanks so much. And let's see the next question. Does Hazelcast have any inbuilt feature to support multi-tenancy?
Yeah, if you'd like to, actually, no. I would, if you'd like to use it for, no. I think if you access like Hazelcast, then you are in Hazelcast, and you just it does not like make any distinction like some per user authentication, etc.
Okay, all right. And then let's see, does Hazelcast support multi-region in cloud? And will there be any negative impact on performance or latency?
Yes, we support multi-region, but you cannot set up like one Hazelcast cluster across multiple regions, because that, that will, it's the same idea, like you cannot set up one Kubernetes cluster across multiple regions, because Hazelcast keeps data in a consistent manner. So if you set it up across multiple regions, your latency will be terrible. But we support multi-region in a sense that we have a geo-replication, and then you create two Hazelcast clusters, one in one region, second in other region, and you set up a geo-replication, which we call one replication in between of them. So it's actually very easy to do it. From the console, you just click create one cluster, create another cluster, and then set up one replication in between of them. But obviously you need to, as with everything with multi-region thing, you need to, one replication is asynchronous. So with all these implications, like, that you have eventual consistency and so on.
Right. Okay, and the next question is kind of two parts. Is there a possibility of a cache miss? And is the cache data on Hazelcast cluster partitioned?
It's like, if you mean by cache miss, that is it possible that you have data in Hazelcast, but it's cached in Hazelcast, but you will from the client see that there is nothing there, but in fact, it's not possible unless you have, because Hazelcast is consistent itself, unless you have a split brain, which means that you have network partitioning, then your cluster becomes two clusters, because we favor, like, you know, this CAP theorem, we favor like availability. That means that by default, at least, that means that you can, part of your application may be in one, connected to one cluster, part to another, and then obviously it can happen. But if you configure this, your cluster to be like, but if there is no network partitioning then the data is consistent, so you will not encounter cache miss.
Great, let's see. The next question is there a viable way to span the Hazelcast instance on-prem and into AWS to support the use case where I have updates coming on-prem, replicating to the cloud, and my cloud API clients need fresh data? Can the cache close that latency gap for me?
Yes, you can do it with the same, what I discussed, this geo-replication, this one, we call it one replication. So yeah, you can do it. I mean, that you have one cluster in the cloud, one cluster on premises, and data is replicated in between of the clusters. So yeah, no problem with that.
Perfect. And then how do you compare using embedded Hazelcast and using Guava Cache?
Yeah, I mean, the main difference is that Hazelcast is distributed, and Guava Cache is like, it's a very good cache, but it's more like it's not a distributed thing. It's like it stays inside your application. So it's one of the first slides you've seen that is the difference between embedded and embedded distributed cache. But if you just need it, you don't need distributed things, then Guava is good enough as a caching. No problem with Guava.
Okay. And then if embedded Hazelcast cluster is used as a cache, can it be configured highly available or highly consistent?
Oh, that's a good question. So it's like, if it's used embedded, can it be configured highly available? I think yes. I think I would need to think about it more, but yes, I think that there is no problem with that. But you need to think about like, because generally there is no difference. I mean, Hazelcast embedded is just Hazelcast server running inside your application. So if you apply the same principles that you would apply to the servers, but to your applications, then it's completely fine. But then your application, if you use embedded, you need to think about in the Hazelcast enabling zone-aware feature and having the same number of Hazelcast instances. So in case of embedded, that the same number of applications in each availability zone. And that's it. And it will be highly available, yes.
Okay. We're running out of time. We'll try and answer a couple more questions. We want to be conscious of everybody's time. Let's see. If you're familiar with AKA cluster sharding, not sure if I'm pronouncing that correctly, AKKA, cluster sharding, is there any configuration that can be used on Hazelcast that emulates this functionality?
Yeah, I cannot answer this question because I'm not so familiar with AKA sharding, so sorry for that.
No worries whatsoever. What we'll do is we will take this to the team and we'll answer via email, and that way we can get you any more information, because as we know, we don't have all the answers all the time. The next one is, can we have Hazelcast map configuration at client side instead of the server side?
You can. No, because like the map is configured on the server side, but you can add a new configuration from the client like this. So, but the configuration itself is stored on the server side.
Perfect. And again, we're running out of time. I know there are a couple more questions. We will answer those via email. We'll make sure that we get those to you. But again, we want to thank everybody so much for taking the time to join us for today's webinar, and want to thank Rafael for such a great presentation. Obviously, there were a lot of questions, so it was very interactive, and we appreciate that. Someone will reach out to you after the webinar to help answer any of those questions that we didn't get to. And we again, go to our website, check it out. We hope you enjoyed the presentation. I am going to post a few resources in the chat panel in case you want. One of them is a link to our Hazelcast guides. It has all the information about Kubernetes and different things that you'd want to find out. And then there's some other resources in there that you might find useful. So just check out the Hazelcast website. You can go to resources or check those guides out at guides.hazelcast.org. And again, someone will reach out and help you out with any of those questions we didn't get to. Thank you so much for joining us, and we hope you all have a great day.
Thank you all from my side as well. Have a great day.
Bye-bye.